Welcome to Q&A Wire.
Okay. So, first off, we've got glycerol. Okay. Now, glycerol is an acid, but it's a relatively weak acid. So let me find its pKa here. Let's see. What was pKa of glycerol? 14.4. Okay. So what's the pKa of water? 14, naturally. Okay. So the pKa of glycerol is lower than the pKa of water, meaning it's less likely to dissociate than water. Okay. And recall that H plus, the concentration of H plus in neutral water is about 1 times 10 to the negative 7. So if glycerol is even less acidic than water, then we shouldn't expect that adding glycerol to water will have any effect on the concentration of H plus. Even if we added pure glycerol, the concentration of H plus would be less than it is in neutral water. Okay, so we shouldn't expect that there'll be appreciable amounts of glycerol. Like, so let's how would I write this, right? Like, so acid dissociation of glycerol could be written like this. Right. We don't expect this to happen to an appreciable amount. So our major species present are just going to be water and glycerol as is, right? And we don't have to worry about H plus or OH minus or anything, or the conjugate base of glycerol. It's not something we have to consider. Okay, now let's consider zinc chloride. This is going to be different, right? Okay. So if we take zinc chloride and we mix it with water, what do we expect will happen? We're going to get zinc hydroxide. I guess I should balance this. Okay. Oh, my bad. No, I don't need that. What's going on? Ah, yes, I do need 2 of these. Okay. Great. Okay, so we will form zinc hydroxide, and when we form zinc hydroxide, the amount of H plus will increase. And remember, you might think, oh, we don't get HCl. Well, HCl will dissociate completely in water, right? HCl is not going to form. The chloride is going to be floating around freely, and the H plus is going to be floating around freely. So the species that we need to consider then is going to be water, zinc hydroxide, H plus, and Cl minus. We'll have appreciable amounts of all of these. Okay, now let's consider potassium cyanide. Okay, so what's kind of interesting here is like, okay, so consider what potassium cyanide is. It's K plus and Cn minus, right? This is part of a strong base, right? What I'm saying is that we won't expect any potassium hydroxide to form, right? Because these will dissociate completely in water. So no matter what happens, I expect that on the other side of this arrow, I'm going to get K plus. Okay, that's all that's going to happen there. We're not going to like start getting potassium hydroxide like we did with the zinc, because potassium hydroxide is a strong base. It'll just dissociate fully, unlike zinc hydroxide. Okay, so now we have to look at what the effect of the cyanide would be, right? So cyanide is acidic. What is its pKa, right? Rather, what is the pKa of hydrocyanic acid? That's our question. And the pKa of this is about 9, which is, a stronger acid than water. What that means is that CN, more so than water, is going to be a stronger base than water, right? So CN minus is actually going to abstract H plus from our water, or you can think of it as is going to react with H2O to form HCN and OH minus, right? So basically, CN minus is a somewhat strong base. That's what we're looking. That's basically what we're going to get out of this, right? So our major species will be water, K plus, that's potassium ion, hydrocyanic acid, and hydroxide. Right, so it's kind of the opposite of the zinc chloride. And zinc chloride, the result of adding zinc is that it abstracted OH, and so its effect was kind of like an acid, increasing H plus. In this case, CN is acting like a base, stealing H plus, and therefore increasing the amount of OH, free OH minus, free hydroxide. Whereas glycerol is too weak of an acid and too weak of a base to do either.